Recording in progress.
All right. It's 7 o'clock. I'll get things started. Welcome to the June meeting of the Southwest Florida Astronomical Society. I'm Brian Risley, the president, and we're going to get right into our presentation, which then we will have the business meeting after the presentation. John, if you want to introduce our speaker tonight.
Welcome to our new 2022-2023 annual speaker series. Tonight, our speaker is Dr. Desika Narayanan, who is an associate professor of astronomy at the University of Florida. Dr. Narayanan received his undergraduate degrees in astronomy and physics from the University of Florida, with highest honors in 2003 and his PhD in 2007 from the University of Arizona. He then held fellowships at the Harvard-Smithsonian Center for Astrophysics and the University of Arizona, and was assistant professor at Haverford College prior to joining the faculty at the University of Florida. Dr. Narayanan's research interests focus on theoretical models primarily related to cosmological galaxy evolution, star formation, and to the interstellar medium. He utilizes large-scale numerical simulations to simulate the interplay between small-scale star formation, interstellar medium physics, and global galaxy evolution. Dr. Narayanan's talk tonight is entitled Forming the Brightest Galaxies in the Universe. Please join me in welcoming Dr. Narayanan.
All right, thank you so much. I hope you can hear me, and please let me know if you can't. So this will be a talk that it's about a problem that has vexed me since I started graduate school in 2003. I wrote my first paper in this area, I think, in 2008. And then I wrote, well, my graduate student this year wrote what I hope is my last paper in this topic in 2023. So it's been a multi-decade effort to understand this problem. I'll spend the vast majority of the talk actually trying to describe what it is that I do as a theoretical astrophysicist, and hopefully introducing the problem via the methodology itself. I don't know the culture of talks at the SWFAS, but you're certainly welcome to interrupt with questions halfway if you'd like. I just may need the person with the microphone to let me know. Okay, so I'm going to start this talk actually in 2011 in June. So in 2011 in June, I was living in Tucson, Arizona, for a postdoctoral work, and I just gotten married. And it's pretty hot in Arizona in June, and so we went on our honeymoon to Chile because I really like snowboarding and I would love the snow, and I really wanted to go somewhere cold. And my wife used to live in Chile, and so we thought it'd be a great place to go. So one night we're at this cabin, and we'd met up with a couple of friends, and in the Andes, and I go outside and I saw this fuzzy blob outside. Side note, I didn't realize until a little bit later there was a wolf outside stalking me. And I looked earlier to see if I could find the picture of the wolf, but I couldn't find it. So yeah, I see this fuzzy blob with my naked eye. And I just gotten this new digital camera because we were pregnant with my older boy, who's actually sitting in the room watching this talk too. And so I just gotten this new camera, and so I thought I'd play with it. So I ran inside and I got the camera and I set it up and I opened the exposure for 30 seconds. And so I opened the exposure for 30 seconds and I see this. So this is now, of course, what we know is the Milky Way. This is our own galaxy. And by opening the exposure for 30 seconds, I obviously was able to collect a lot more photons and reduce it from a noisy image like this to something much clearer like this, something I'm sure many of you are very familiar with. Okay, so this is our Milky Way. This is the view of the Milky Way we have anyways, because we are located where this red dot is. This is an artist's impression of what we think the Milky Way looks like based on our data. We'll never be able to fly out of the Milky Way. The distances are too vast. And there's sort of three major components of things that we can actually sort of see. And by that, I mean not counting dark matter and dark energy. There's a supermassive black hole at the very center of the galaxy. This represents less than 1% of the mass of the galaxy. 90% of the mass of the galaxy is made up of stars, and we form something like 1 or 2 new suns every single year. And then the rest of the galaxy is made up of gas and dust. Dust has a kind of unfortunate name because it has a negative connotation here on Earth, but it's actually one of the most amazing things in astrophysics. They're really just complex organic molecules, and a lot of this talk is going to be about dust. And I hope to convince you, even though it sounds terrible, and that's why I don't put it in titles, dust is actually super cool. So this is actually one of the more recent images of the Milky Way from the solar neighborhood from a satellite. And this is a map of the Milky Way. And what you can see actually toward the center, this is the galactic center here, and you see these dark spots here. And these same dark spots, if you look now in the image that I showed you here, they show up here as well. You see these places that are a lack of light. So these dark spots are not actually a lack of light, but what they are giant clouds of dust, these heavy molecules floating around in space that actually absorb all of the starlight. So it's almost like if you were, in a room and shining a laser pointer at me and I put in chalk dust from 2 erasers, it would block out the light, or like a fog and headlamps in a car. And so dust is these giant dust clouds that weigh like 1,000,000 times the mass of our sun is sitting there and blocking out this light in our Milky Way. This is going to be critical to this search for the brightest galaxies in the universe. Okay, so that's our Milky Way. We live in an incredibly rich universe. It's a wonderful place. Every movie I show you today is going to be fake. They're going to be theoretical simulations, except this one. This one's real. Now, obviously, it's a reconstruction of observations of the neighborhood around the Milky Way, around our own galaxy, but they are actual observations of real galaxies. And it's just astounding, right? I mean, it's so humbling to think about your daily problems in Fort Myers or in Gainesville or wherever you may be calling in from, and then to think we're just sitting on this one planet and there's billions of suns in our galaxy, and then you just see all of these galaxies. And the crazy thing is, this is just like a very, very small percentage of the universe. This is from a survey, the Sloan Digitized Sky Survey, and the wedges are artifacts of the survey design. It's not, galaxies are isotropic around the universe. But it's just an unbelievable richness of galaxies. And we see, when we zoom in on these galaxies, these are all real life images. And I have to distinguish that because we're going to look at a lot of fake images in this talk as well. We see an astounding amount of diversity. So this is the Pinwheel Galaxy, and you can see, again, these blue is the starlight, and then the areas here are dust clouds that are blocking out starlight. We see this a little bit more prominently when we look at some galaxies in an edge-on configuration. We see galaxies out there that are interacting. So these are 2 galaxies that are merging together. Again, something that's going to feature prominently later in this talk. And we see galaxies that even have crazy outflows. So this is a galaxy where a supermassive black hole in the center is driving massive amounts of material way out into the intergalactic medium. And if you just took a sort of diversity, like a yearbook, I guess you could call it, of galaxies in the very nearest universe. I mean, these are right, these are just in the solar neighborhood. You see, they're just like people. They come in different colors and shapes and sizes and personalities. I mean, and this is really the charge for the galaxy formation astrophysicist, is to understand and develop a comprehensive physical theory that could connect and understand why these galaxies all look the way they do. So we're going to come back to this in a second. Okay, well, I like giving public talks sometimes because the audience is more my age and less, like college students. Because when I talk when I talk about things like this to college students, they look at me like I'm a crazy old person, because I have to now go back to the 1990s. Sorry, is there a question? No, I think it's just an unmiked.
That's the only way I can do it.
Okay. Does someone have a question?
Get there.
We're handling it at this end.
Speaker's the one that's on right now.
I'll figure it out. Okay, there you go. Okay, so in 1994, we launched the Hubble Space Telescope. Sorry, my computer's actually, let's see if I can, my computer's frozen. Give me 1 second. Okay, there we go. So in 1994, April 26th, we launched, or April 24th, we launched the Hubble Space Telescope. It's still one, we're in cycle 31 now, 31 years in. I'd actually just submitted a theoretical proposal for it last week. And it's still ultra competitive, 10 to 1 that you won't get time on it. And so it's so valuable. And when the very first director of the Hubble Space Telescope, every director gets what's known as discretionary time to do whatever they want with the telescope. And this director, he says, I'm just going to stare at the blankest part of the sky that I know about. And everyone's like, what are you doing? Why are you wasting this precious time? And so he held the shutter open for days and days and days. And, everyone's like, you're wasting all your time. And when they downloaded the data, this is what they saw. They saw what's now known as the Hubble Ultra Deep Field. And just like in the local universe, it's an incredibly rich diversity of galaxies. And, the fact that we were looking in a completely blank part of the sky where we knew about nothing, just like my Milky Way picture from when I was on my honeymoon, if you open the exposure for long enough, you eventually start to see stuff. Now, unlike the local galaxies that I showed you, these galaxies are going back to near the beginning of time. So this is a cartoon picture of the universe. On the left here is the Big Bang. This is 14 billion years ago. And then this satellite is a picture of today. So this is 14 billion years later. These galaxies go back to about 2 billion years after the Big Bang. And we're going to talk a little bit later about how James Webb is actually going to getting to, a few 100 million years after. But, these galaxies are, at the time, were the earliest galaxies people knew about, and people didn't know galaxies even existed that long, that soon after the Big Bang at the time. So now we have this incredible rich pageantry of galaxies that we see in the local universe, and we also have a similar diversity in the early universe. And this just exponentially increases the challenge that we have as galaxy formation astronomers to understand how they all connect. And the analogy I give is, say you took a picture of me, and maybe you say, okay, that guy looks kind of like a monkey. And then you can look at cavemen and you say, well, they look kind of like people, but they also look even more like monkeys. And then you look at actual monkeys and you look at things that are variants of monkeys, like orangutans. Well, you could say, well, there must be some physical scenario, biological scenario that connects all of these at the same time. And that's the job of the galaxy formation astronomers, to understand how do we connect these galaxy populations in the very, very early universe and the diversity that we see to those that we see today. It's really quite the same. So there's two kinds of astronomers. There's observational astronomers. That's the kind you traditionally think about. That's like, hold on one second, you gotta be quiet, buddy. That's like, the people who go to the telescopes. And then there's computational astronomers, and that's what I do. So what do we actually do on a day-to-day basis? Well, we play mostly with big supercomputers instead of big telescopes. So this is our own supercomputer here at the University of Florida. It's called Hypergator. It's 70,000 computers all working at once. It's an incredible machine. It's one of the top 2, I think, or maybe the second best university computer in the country. I've been all over the place, like at Harvard and Arizona and these major universities, and nothing compares to this computer. Even the NASA computers aren't as good as the one we have here. It's really quite incredible how the investment they've put into this here. So if you look at these computers, you can see that there's these little like racks here, right? That they and so these little racks, if I zoom in on them, so this is what if I zoom in, this is what the racks look like. They're kind of like big laptops, and each laptop might have like, they're bigger than that, but they might have like 64 or 128 computers on them, and they all connect via an Ethernet that's way faster than anything you or I have access to each other. And so you have your computers all talking to each other and working in unison, so that, like, if you're working on, imagine just working on a simple math problem in high school or college, and you might use a calculator. Well, then the kinds of problems we're working on here would take millions and hundreds of millions of years for one human being to do on a calculator. So you deploy it on thousands to tens of thousands of computers at once to do it in a human lifetime. And, it's fundamentally, it's actually not so hard. In practice, it's really challenging. But you have equations that you learned in high school and in college. You might have learned, like in high school physics, F equals ma, or F equals gm1 m2 over r squared. That's your force equations. You have fluid dynamics equations that govern how fluids and gases interact with one another. And then you have radiative transfer equations that govern how light goes through media. And you just plug it all into a whole lot of computer code and you press go and you see what happens. So this is a movie actually of it's one of our new state-of-the-art simulations that we're developing here at University of Florida that shows sort of what we actually do. So this is an example of what we think the Milky Way is doing. So we started off with some set of initial conditions, and what you're seeing is the gas in the galaxy. And then every time enough stars form that you get a massive one and it explodes, it dumps a bunch of energy into the galaxy, and it creates these little holes here. And we start to get these this very clumpy Swiss cheese morphology to the galaxy. And we can use this then as like a numerical toolkit to investigate a range of problems. For example, how do you form the earliest galaxies in the universe? Just as an example. Okay, so we've gotten, over the years, incredibly sophisticated in how some of these simulations work. As an example, this is a set of 11 images of galaxies. 3 of them are fake. 3 of them are ones that we generated in our computer, and that I've made the color scales look sort of the same as these observed ones with the Hubble Space Telescope. And you could take a minute and look and see if you can identify which ones are fake and which ones are real. If you stare long enough, I think maybe you'll figure it out. But it's these 3. Are the fake ones. And actually, I made a mistake in doing it, and you can see that there's background stars here, and I forgot to put them in the fake ones. And that's actually a quick way you can find them here. Okay, so now, with that, let's kind of turn to the actual main topic du jour. How do we form the brightest galaxies in the universe? Okay, so I have to now shift gears a little bit from what we've been talking about and talk a little bit about the nature of light itself. So this is a telescope. It's not like the telescopes you're used to seeing, that the ones you probably get to enjoy on when you go observing, or even just the bigger versions of those that we have on Mauna Kea or in space. This is a radio telescope. We actually call it a sub-millimeter telescope, and I'll tell you why. Back when I started graduate school, this is on top of Mount Graham in Arizona. I used to be an observer, and I used to spend a lot of time here. Just in the bottom here, this building, there's a bunch of dorm rooms, and then you climb up the stairs, and back here there's a control room, and it was a ton of fun. And so this sort of telescope works really differently than a glass optical telescope that you're used to. This is the electromagnetic spectrum. So light has a wavelength to it. Everything we see right here on Earth is right here in the visible. This is sort of at 5,000 angstroms. Then if you go to shorter wavelengths, you have the ultraviolet, the stuff that burns you if you go out to the beach for too long. Then you have X-rays, and then you have gamma rays and cosmic rays. And then on the longer, lower energy side, we have infrared, and then eventually we have microwaves and then radio waves. It's in this infrared region here, the region that we can't see with our eyes, but animals can with night vision, that I'm going to concentrate. And it's this wavelength regime in the infrared here that these telescopes like this, that we call the sub-millimeter telescope, are intended to work at. So all the telescopes you're used to work here in the visible, the range that our eyes work in. So the reason, just as a side note, the reason our eyes work in the visible here is because the sun peaks, all of its light comes out in yellow and green. And so just over however many billion years of evolution, humans have evolved to see in the wavelengths that the star that we have emit at. You can imagine if we lived around a hot star that emits most of its light into ultraviolet, we might see very differently. Or conversely, in a low mass star, we might see it in the infrared instead, but we don't. Nonetheless, there's information at all of these wavelengths. And astronomers use all wavelengths accessible to be able to try to understand the astrophysics of the universe. So why do we care about infrared light? So what can happen is if you have stars, stars emit most of the light in the optical and the ultraviolet. And like I showed you in some of those galaxies, sometimes that light can be blocked out by dust. Now, the thing about dust is it's really cold. It's like 100 Kelvin, 100 degrees above absolute zero, whereas the stars are like 5,000 Kelvin. So what happens is the light hits the dust and it heats this dust up just a little bit. And then that dust absorbs the energy and then it emits that light back out in the infrared. And the reason is because colder objects tend to emit most of their light in the infrared. So all this light that was blocked out by the star, by the cold dust, is now emitting in the infrared. And so by looking in the infrared, we can see information that was once hidden to us by the dust blocking out these stars. And so that's why we build telescopes like this, to be able to see in the infrared and to be able to see past the dusty clouds. Okay, hold on 1 second. You may not. Yeah. So what happens in a galaxy if I'm blocking out all this infrared light? Well, let's imagine I had a galaxy that had, this is only one of very few technical plots in this talk. Let's imagine I had a galaxy that had no dust at all. Do you mind turning the fan on, Ashwin? It would look like this. So this axis here is wavelength, and then this axis is brightness, luminosity. It would look like this black line. Most of the light would come out in the optical and the ultraviolet, here at very short wavelengths that our eyes see at. But what happens when I add dust to the situation is this light all goes away, it gets blocked out, and instead it gets re-emitted into the very cold regimes, into the infrared. So this is why we build telescopes in the infrared, to be able to catch this part of the galaxy spectrum and understand what else might be happening out there. Okay, so let's now go to I think 1998. So in 1998, the Europeans and the British built a new submillimeter infrared telescope on Mauna Kea, and they called it James Clerk Maxwell Telescope, JCMT. So remember when I showed you the Hubble Ultra Deep Field, it stared at this blank part in the sky and it showed all these galaxies. Well, since then, literally every single telescope, every single one, has stared at this exact same spot in the sky to see what it can see. Every single one. And the James Clerk Maxwell Telescope is no exception to this. So it stared and stared and stared, and this is what it saw, which at face value is kind of underwhelming. I mean, when you compare it to the Hubble Ultra Deep Field, where we saw thousands of galaxies, at best you could convince yourself that maybe this is a galaxy. It's actually the brightest galaxy in the universe. This is a galaxy. It only saw like 5 things compared to thousands, and they look like fuzzy blobs. So at first you think, oh man, this is just not that interesting, right? Like compared to the richness we see in the optical. But it turns out these galaxies, which we call submillimeter galaxies, because the wavelength we catch them at is just short of a millimeter. So, very creatively we call them submillimeter galaxies. Are incredible. They're the most, these galaxies that the JCMT found is by staring at the Hubble Ultra Deep Field are some of the most incredible galaxies in the universe. So just as a comparison to the Milky Way, let's just look at some numbers. First of all, the Milky Way is about 20 billion times the brightness of the sun. That's what this means. These are 10 to the 14, so they're 10,000 times brighter than the Milky Way. They're about 100 times more massive than the Milky Way, which is 30 billion times the mass of the sun. And these are like 1 billion times the mass of the sun, or 1 trillion times the mass of the sun. The Milky Way forms like 1 sun per year. Submillimeter galaxies form more than 1,000 suns per year. And the crazy thing is, it was doing all of this when the universe was in its nascency at 10 billion, just a few billion years old. Whereas today, we're 14 billion years in the evolution of the universe, and our own Milky Way is so puny by comparison. Taken together, submillimeter galaxies are the brightest and most luminous, and most heavily star-forming galaxies in the universe. And since they were discovered in 1998, it has been a huge problem for astronomers to understand what are they, like what makes these things tick. And so we'll start off where I started off. In 2006 or 7, I started off with a guess, an ansatz is a hypothesis, that the submillimeter galaxies are mergers between galaxies, or 2 galaxies that have smashed together. That was my guess when I was 28. Why? Well, if I look in the local universe, the brightest and most heavily star-forming galaxies also are all mergers. These are real-life galaxies, And if I look around and I try to ask what about the brightest galaxies, they're all mergers, every single one of them. So why not in the early universe? That must be true too. So let's see if this could be true. So what I do is I'll take simulations of two galaxies and I'll smash them together just to see what happens. So this is an example of one of these simulations that we ran. You're seeing the colors. The colors are the gas temperature. So pink is cold and then blue and white are hotter. What happens is once these galaxies go through their first passage, they come in for a final coalescence. And when they come in for a final coalescence, through a range of just mechanical reasons that you learn about in college mechanics, they sort of spin up and the conservation of angular momentum, they end up driving a bunch of gas toward the center. And when they do, they go through what's known as a huge starburst event, where we form tons and tons and tons of stars per year. Tons, like hundreds to thousands. So it seemed like a reasonable thing to be the formation mechanism for submillimeter galaxies. And so if I actually plot this up, now I think we got around to publishing this in 2010. Just look at the blue line here. And this blue line here is the star formation rate, and it's normalized to like 4,500 solar masses per year. This x-axis is time, and the y-axis is whatever quantity I'm plotting. So in this case, it's the star formation rate. And they go for their first passage, so they look like this. And when they come in for their final coalescence, they go through this huge boom of 5,000 solar masses per year. And we think, great, this is an extreme example, but it works. They're as heavily star forming as submillimeter galaxies. This must be what's going on. And we wrote tons and tons of papers on this, and it attracted sufficient attention that I got my first faculty job out of it at Haverford College, and it was really great. I'm actually going to skip this slide here. It's not that useful. But then I was a few years into this faculty job at Haverford, it's outside Philadelphia, just in 2014, 2015, and we started looking into this a little bit more and trying to really round this model out and ask, is this really the whole story? And we asked, is every submillimeter galaxy a galaxy merger? And unfortunately, the answer was no. I mean, fortunately in some ways, because it kept me going, but unfortunately, because I thought I'd solve this problem. And so why? How can we demonstrate this to ourselves? Well, what I ran before were just sort of somewhat simplistic calculations where we just banged two galaxies together that I set up by hand. Now, if I run a different kind of simulation where we evolve entire chunks of the universe at once. So in the time at the bottom left, you can see time since the Big Bang. This is what's known as a cosmological simulation, where we're now simulating just sub-volumes of the universe all at once to see how galaxies form in aggregate, like within the environment of the entire universe. We can start to investigate whether these mergers are really what's driving these submillimeter galaxies. So what you're seeing now is the time when submillimeter galaxies would really live, a few billion years after the Big Bang. So you can start to see gases collapsing into the nodes of these filaments, and eventually you start to see these things, I hope, that look like fireworks going off. And these are actually supernova exploding and driving gas back out into the galaxy, and star formations happening. It's a really incredible and violent time in the universe. The universe, a few billion years after the Big Bang, is like a human being in their early 20s. I mean, there's just no stopping them, right? We live now like a human being in the 60s and 70s, like very wise, very evolved, but maybe not quite as much energy as what's going on a few billion years after the Big Bang. So it's a really incredible time. So it makes sense that this is why submillimeter galaxies would live then, when they form stars so rapidly. But the problem is, if you go in and you count the number of galaxy mergers, there's just not enough of them. No, there's not enough mergers in the universe. We proved this to ourselves around 2013, 2014, by plotting just a very simple thing. We took all the observations, that's these gray dots here, and plotted the number of galaxies against their brightness. So these are the brightest galaxies here. There's not that many of them. Then these are the least bright galaxies. They're still pretty bright. There's a lot more of them. And we took all the mergers in the universe that we could find in these simulations, and you underpredict. You're just not there. So this was a little disappointing when we didn't really know where to go from here. So with some thinking and, talking to people and trying some different things, we decided to run a different kind of simulation. And this is one now where instead of running these idealized mergers, instead we run simulations like these cosmological ones that I showed you before, these ones where we take the whole chunk of the universe, and then bit by bit, we would go in and splice out individual galaxies that are forming and re-simulate them in much higher fidelity. And when you do, you catch a lot of interesting physics that we didn't quite catch the first time. So this is one of those simulations now. It's called a cosmological zoom-in simulation. And this is a formation of the Milky Way model. So we're now a few billion years after the Big Bang. The units on the left have to do with the expansion rate of the universe. It's not actually time. And you can see that there are clumps of gas merging in, but it's not really the same thing as this very simplistic picture I showed you where you smash two galaxies together. Rather, it's a messy environment. It's like it's just really crowded, right? I mean, there's just all lumps of gas everywhere. And even the mergers themselves, like this green lump of gas falling in, it's not the same thing as these two mergers that I showed you, which are rare events. Instead, what you're seeing are just little clumps of gas in a very, very rich environment. And that's what we think we're actually seeing. And if I was to zoom in on this and actually then go through some calculations to make it look like what we think you'd see with your eyes, if you could see this, this is what you'd see. You'd see maybe a galaxy as well formed in the center of its dark matter halo. But then you see all sorts of other things. You see a neighbor here, you see a neighbor in the background there, you see a couple neighbors here. You see just a ton of what we call satellite galaxies. And each of these satellite galaxies is contributing to the light we see. And so instead of these big mergers, what we think we're actually seeing are just very messy environments where you're counting in any one observation many galaxies that are just getting smeared out because our telescopes are, at the time in 1998, were not good enough. And so what we think, this is now a theoretical prediction, we'll see, if we were able to look at these smudges, which are the brightest galaxies in the universe, and if we were able, with bigger and bigger telescopes, to be able to pull these images apart and see the details, we think we'd see something like this. We think we'd see lots and lots of galaxies all near each other, but not necessarily merging just yet. And this is sort of an image of what that would look like. Little satellites all around big galaxies like this. So I'm actually going to skip past this plot here and ask, is this even provable? Well, actually, let me know. I do want to go back through this plot because this is where I think we're wrapping up this story a little bit. So in 2021, I worked with a postdoc in Hertfordshire in England, and we created one of these mock universes. And what we did is we took a simulation, one of these cosmological simulations, and we faked well, it wasn't faked, it was through very heavy calculations with a supercomputer, what the light from these galaxies would look like. And we mocked up what we thought a survey would see. And these are the sorts of stripes that we think the surveys would see as they look further and further back in time. And when we now compare the abundances of these model galaxies to the true abundances, so this is again now in science units, number versus brightness here. And we compare the old model, which is this orange line, to the observations. Well, it didn't do so well. And if we compare this new model here, we do much better. Now, the problem's not still solved, unfortunately. This is just as close as we've come so far, but we're within a factor of 2 now, which is much better than we ever were before. We were a factor 100 off. So it's almost enough that I think we could call it a closed deal. And to be honest, I don't know what's driving this factor of 2 difference at all. It could be something to do with the dust physics that we included, but I'm not really sure. But it's close enough that I think we can dare to make predictions and dare to say, well, this model's probably right. And if it's probably right, what are the sorts of things observers might see? So, I showed you the Hubble deep field near the beginning of this talk. I showed you the submillimeter deep field. Well, about 10 years ago, and I show this now because even though it's 10 years old, it's still one of the most magnificent facilities we have on the planet Earth. We built in collaboration with the European Space Agency? No, European, I don't know, the European Astronomer Organization and Japan. The Atacama Large Millimeter Array. So this is high up in the deserts, in the Atacama deserts, 15,000 feet above sea level in Chile. And instead of one telescope, now we have 64 telescopes, all working in unison. So their collective area is to observe things is so much greater than any one telescope that it can actually start to pick apart some of these blobs that we were seeing before. And now when it looked at the Hubble Deep Field, the same as all these other telescopes did. And what it started to see is this area here is what we used to think was the submillimeter galaxy. And now we see it actually does break up into multiples. And almost every one of these is just multiples, not quite merging, but just these very rich dark matter halos that are super bright, which might be a vindication for this theoretical model. Maybe. Okay, so where's the future going? Maybe it's the last couple of slides I'll show you, and then we can take some questions. Well, undoubtedly, you've been as excited about the James Webb Space Telescope as I have been. It is a marvel of human engineering. To be able to put something up like this on Christmas Day and ship it off 1 million miles from Earth and have it unfold like this. And the thing is, it's working better than we expected. I'll give you an example. So NASA quoted a mission lifetime of 5 years. Just, a CYA policy in case it didn't work so well. $10 billion, you hope it's going to work better than 5 years. But really, astronomers all thought 10 years. 10 years, and we thought, well, 10 precious years with this telescope if it works right. Well, on their way to L2, which is where it's parked, they saved so much fuel by getting the mid-course corrections so well that they were able to actually extend the lifetime to 20 years. And it's just thrilling. I mean, I love it because it's the end. It'll take me to the end of my career. And it's just such a wonderful telescope. Oftentimes, we say JWST stands for the Just Wonderful Space Telescope. It's really incredible. And unfortunately, we're only 18 months into observations. And so there's really not yet definitive results for how this can shape our understanding of these earliest starburst universe formation. But I'll give you a little teaser of what we think we're going to learn. And it's that the universe is even brighter and even richer than we knew before, which is hard to believe. So a couple of friends of mine, Caitlin Casey at UT Austin and Jehan Kartal-Tepe at Rochester Institute of Technology, are mapping the same area as the Hubble Deep Field. So this area here shows how big of a map that they're doing. And then if you just take this little inset, this tiny little inset here, and blow it up, you see the richness of the universe and how absolutely stunning it is. And if you zoom in on just a few of these galaxies, you see they have the same richness and diversity as all the other galaxies in the universe that we've observed so far. But now, instead of 2 to 3 billion years after the Big Bang, we're getting to 0.2 billion years after the Big Bang. These are truly the first galaxies that are forming. The very first galaxies. And we're finding things that are going to puzzle us for the rest of my career. These galaxies are already 100 times more massive than our own Milky Way, or as massive as the Milky Way. 0.2 billion years after the Big Bang, we're now 14 billion years. We have no clue how to make them so massive. They're forming stars at hundreds to even 1,000 suns per year, 0.2 billion years after the Big Bang, the same as these submillimeter galaxies. And our models are not yet caught up. So if you ask me to come back in 10 years, in the year 2033, I'll have an entirely different talk to give about how we spent the last 10 years chasing the results that the James Webb Space Telescope is giving us at the very dawn of time. So, with that, I'll leave you with maybe some concluding thoughts. If there's one you take away, it's that every time we get a new telescope, even I have to admit, I was skeptical when James Webb went up. I was like, what more can we learn? Are we just sweeping the corners for details? And it's not true. I mean, there's generations of careers of astronomers of information out there. The universe is so much richer and more mysterious than we can possibly imagine. Every time we look, it makes us have to rewrite the theories from scratch. And what's incredible is if you look in the early universe, things are not like they are today at all. And it's that much more complicated to try to understand how we connect those ancestors of our modern day galaxies to what we see today. But our methodologies are getting more and more sophisticated. We're now talking about in the 2040s building a version of the Hubble Space Telescope. The Hubble Space Telescope is 90 inches across. We're talking about 2.3 meters, is that right? Something like that. We're talking about building something 10 times bigger that's near Earth and serviceable for, you know, around 20 years from now. It'll be expensive for sure. I mean, the initial costs are 10 billion. It'll balloon to 50 probably. You know, that's the cost of. As an example, Americans spent $10 billion on Halloween costumes last year. So, you know, in perspective, it's not that big a deal. And a combination of that plus our supercomputers, I think it's going to be an exciting next few decades as we learn more and more about the very early universe. And with that, I'll end, and I'm happy to take questions as long as you have them.
All right, let me get some lights on in here so I can see people. If anybody online has a question, go ahead and ask it. I'll get some lights up. All right. Let me start over here with John.
Hi, a couple of two questions. Number one, you mentioned that you're trying to put together, an evolution as to what happened to these guys from 200 million years after the Big Bang to today. Can you expand a little about what you think is in terms of the evolution as to what we would see? You know, what's left? How does what we see today relate to what it was 200 million years after the Big Bang? The other thing is, when you put all the physics together and the models, there's a huge unknown, right, that's come up that wasn't there 30, 40 years ago, which is this dark energy, dark matter. Is that likely to really mess things up or really be part of explaining why, the models of standard physics don't explain it all?
Those are two great questions. So I'll start with the first one and I'll repeat each one as I give them. So the first question is, can I expand a little bit on what we think about the evolution of galaxies as they go from the very first ones in the universe through today? So, I don't think I really have to explain this to the audience, but, just in case there's a couple of newer members to your club, when we look further and further back in the universe, we're looking back in time, right? So we're looking closer and closer to the Big Bang. So we actually are looking, when we look just a few billion years after the Big Bang, at the ancestors of galaxies today. And when we look at these galaxies that are the ancestors of galaxies today, they don't look like galaxies today, obviously. It'd be like looking at our own ancestors, monkeys, and trying to understand how they look like us. Well, they don't. So you have to kind of look at, to be honest, we have to play a number of different games. So from a theoretical standpoint, I can just evolve the simulations forward through today and see what they might look like. But you might say, fine, these are just theories. Who knows if you're right or wrong? So what would an observer do? Well, an observer, what they would do is they would look at the abundances of these galaxies and say, well, these galaxies are sufficiently rare that I can map them to another type of galaxy that's sufficiently rare today, and maybe they're probably the same sorts of galaxies. And what you ultimately find is that when you look at these very, very earliest universe galaxies, while they may look like real galaxies at the earliest times, like big spiral galaxies, etc., today, they're really huge, massive, dead galaxies. So they might be about 1,000 times more massive now than they were then, because they kept forming new stars and accreting new material over all of cosmic time. But what usually happens when a galaxy gets to be too big is that a black hole in the center of it throws all the material out and kills it all. So I'll kind of play a movie here to show you a little bit of what I mean by that. This is the wrong movie here. So this is that illustrious movie I showed you. And if I fast forward, we start to see these explosions happening. Some of these can happen when you get very, very big billion solar mass black holes in these galaxies, and they dump so much energy into the galaxy that they kill off all new star formation, and they kill off all of the light, all of the sources of new light. And the galaxy just sort of passively fades into a very, very old and dim galaxy. And we see those today, so we think that's what the connection probably is. But, doing that quantitatively and mathematically is very hard. Two, the question is, how does, we have all these computer models, they look fancy, I might be able to convince you they're right. How does the very, very heavy unknowns of dark matter and dark energy factor in? And it's a good question, and it's one that it's easy to be skeptical of, because dark energy is like 75 or more % of the mass energy budget in the universe, and dark matter is like another 20-something%. So you're talking about what we can see that we think we understand is like a few % of the universe, and most of it we don't understand. We don't know what dark matter is at all. But we have maybe some constraints. We can say, well, it's some particle that is lighter than some mass. With dark energy, which is this mysterious force pushing the universe apart, we actually don't know anything other than its observational characteristics. But that said, we're able to know about their effects quite a bit. And what I mean by that is when Vera Rubin 50 years ago first discovered dark matter, she did it by seeing the gravitational effects of dark matter on the Milky Way. And now, in the 50 years that have happened since then, we have a very, very good understanding of how dark matter interacts with things gravitationally. And we know to a fairly high certainty how much dark matter there is in the universe. Similarly, while we don't know at all what dark energy is, we know very, very well what it does to our equations. And we know very, very well, to a high degree of accuracy, how strong it must be. So even though we don't know what it is, we can still put it into our mathematical equations and evolve things forward with some high degree of confidence. So there is a little bit of a philosophical question here that ties into how you do these sort of theoretical calculations. And that is, you do always have to make assumptions. There's always stuff you're putting into these simulations that you don't really know how it works. We don't really know how stars form. We have a good cartoon picture of it, but a lot of the details we don't really know. So you have to put in these prescriptions in these models for how you think stars are forming. And then what you do is you don't study in the simulations how stars form, because you put in some prescription. You instead study that effect on large-scale structure, on galaxies, on the evolution of the first systems in the universe. And you say, well, if I'm putting this in by hand, I'm not going to study this and claim victory. I'm instead going to say, this is my assumption, and now let's see how this impacts the rest of the universe. So in that same spirit, we would never say, we understand dark matter, we understand dark energy, but we can say what we think the effects will be on our simulations.
Good evening. I noticed in the illustration that you have for the universe that it's conical. You mentioned the cartoon depiction. Why is it not depicted more spherical? And that would lead to my second question of, when you mentioned that about the 2 billion year mark for the massive amount of the size of the galaxies at that point, would not an explosion in a spherical vacuum distribute more of its mass at the center versus the farther you get out within that same spherical explosion, to show that you would have greater distribution and less dense galaxies?
Those are two very good questions. So the first is the depiction of the universe. So I'm going to actually share my screen again, and I'm going to show you two different things. One is this one. So this one is just an artist impression. It's not at all meant to mean anything. So it's just, an artist impression came out with a satellite WMAP in the 2000s. I did show one other that you may be thinking of as well that I want to look for. Where are you? Here you are. And these were some simulations that we made where we looked backwards in time. And so, for example, this is today, and this is like halfway back in the universe. And here we actually do simulate it as conical. And that's because it turns out through just the geometry of the way telescopes look in the sky and the way light funnels to the Earth, what we see is actually a conical beam of light, or a conical region where light is coming from. That's not the geometry of the universe. That's just an artifact of you looking out with your eyeballs and seeing more and more light funneling in toward you. To get to your second question, which, I can play this movie again just to sort of emphasize some of this. I can show, I can show this one, which has explosions in it as well. It's all sort of the same thing. The question was, when you have these explosions in these galaxies, would you not expect them to redistribute the matter in a way that is less dense in the center? And in fact, that is very true. That is a great question, a lot of insight. And in fact, so we call these processes feedback, negative feedback, where once you form a star, it actually impacts the galaxy in a negative way by dumping a bunch of energy back into it, like you're seeing now. And in fact, 15, 20 years ago, we had basically no models for feedback. About 10 years ago, we had some decent models for black hole feedback, but nothing for stars. And only or maybe it's 15 years ago, and only in the last few years do we have good models for star feedback. And when we've implemented these models in the last decade plus, we found that they actually solve a lot of problems about our understanding of the density profiles in galaxies, why they look a certain way, where they can sometimes be evacuated in the center and then have more material toward the outskirts. This is especially true in low mass dwarf galaxies, where these explosions can have a much bigger effect on the galaxy than in very massive systems. So that you're 100% right in your intuition there. And in fact, these explosions have helped astronomers at large solve a number of problems with galaxy formation.
All right, let me get over.
This question may be a bit on a tangent from the very large to the smaller. Galaxy formation seems to lend itself toward disks. The infall, the angular momentum tends to form a disk, whether it's barred or even or whatever. Some of the oldest star groupings in our own galaxy are globular clusters. They tend to be spheres. And they've been there a long time, or at least the stars have been there a long time. Why do they stay spherical, and yet we almost never or never see spherical galaxies?
It's a really good, really insightful question. We do. The answer is actually with the relative age of these systems. So globular clusters, generally we think are, systems that formed in the same parent molecular cloud. The stars there dynamically interact with one another like billiard balls, but they don't touch each other, but the gravity does, in a way that it's very quick for them to sort of lose their memory of their initial formation and puff up into these spheres. And you can sort of prove it through orbital mechanics equations in graduate school. But it basically, when they sit there and interact with each other dynamically, you start to end up in a situation where they'll puff up into a sphere, and you'll get some interesting things where you'll get the more massive ones in the center and the least massive ones on the outside. Galaxies eventually do that too. The thing is, galaxies have gas for much, much longer. And the reason is because it's falling in from the intergalactic medium. So these clouds in the galaxy are not continuing usually to get more and more gas, but you can see, stop that. You can see at the centers of these galaxies here that more and more gas is falling in from just the universe. And the thing about gas is that gas very quickly loses gas interacts with stuff in a different way than solid material like stars do, and it is more prone to pancaking out and forming disks. And so while a galaxy is young, you do tend to see a very disk-like morphology, but then as the galaxy gets older and older and it's consumed all its gas and more stuff falls into it, it does eventually actually form a spherical system. And if I go back to this cosmological movie here, and I play it forward, you'll actually see it. So let me, if I zoom toward the end, so you can see these galaxies here. Now, if you could zoom in, you'd see that they were disky. But then if you go all the way to the end, a lot of them, stop. A lot of them actually, oh boy, it's hard for me to do this while it's playing, but a lot of them start to look a lot more spherical. And that's because the ones in this movie formed at a very early time in the universe. And so they're sort of devoid of gas, and they've had a lot of time to sort of balloon out the way the globular clusters do. So it really has to do with the relative ages. The globular clusters are much older than the average. I mean, even though they're in our Milky Way, they're the very first things that formed in our Milky Way. And regular star clusters that you see don't yet look like that, but they will in a few billion years. That's an outstanding question.
Thank you. Anybody online got questions? Okay, how about in here? Anybody else have a question? I don't see any. I do thank you. It's a very excellent presentation.
I had a lot of fun, and I hope to be able to see some of you maybe in a visit sometime. Thanks.
Thank you.
Thanks again. I really appreciate it. It was a great crowd, and you know, hopefully in a few years I can come back and talk about JWST stuff.
That'd be great.
Okay, have fun all. Bye.
Thanks. Yeah, that was a very good presentation.
Continue recording.
I don't see any need to.